All right, gang, in our last video, we had this scenario where essentially what happened is we had the same setup. We had 1 plus 1 over n to the nth. And what happened was as n got bigger, this thing kept getting really close to this number here, this 2.718, which actually is we give it a name. It's the constant e, lowercase e. And in fact, that's a limit. It's defined, this is the way, and we're starting to look a little bit like calculus. E is defined, that equal sign with that third bar means defined to be the limit as n approaches infinity. So as you keep putting bigger and bigger numbers in, this rational expression here to a power it keeps approaching a certain number. It's about 2.718, but it's a lot like pi. It's just an irrational number that goes on forever. So if you look at it turns out that we have something in finance called continuous compounding. Like instead of your bank account compounding the interest quarterly or monthly or daily, what if it compounds continuously, like an infinite number of times in a year? You know, you don't actually get an infinite amount of money. That's kind of what we just proved with this magic bank account. In fact, what happens is the amount becomes this. So for continuous compounding, that's our expression. It's kind of easy to remember because of PERT. PERT used to be a shampoo, but it's PE to the RT, where E is that number 2.718. So what do these problems look like? Well, pretty easy, right? You know, what if you had a principal of $5,000, an interest rate of 5.6%, you invest in it for 20 years with continuous compounding, you know, like anything in math, copy down the formula, there it is, PE to the power RT, fill in your principal, $5,000, right? E, and you don't bother writing 2.7. It is the number 2.718, but E is built in your calculator or any computer calculator as well. The interest rate, 5.6%. Don't forget, you got to change it to a decimal, otherwise you'll be off by millions of dollars. And the time is 20 years. And if you jam all this in your calculator, again, pause if you want to try this on your calculator, you get over $15,000, 15,324.27. Just so you know, you can't walk into your bank and demand continuous compounding. This is like a theoretical thing. This is the most bang for your buck at a given interest rate. So, you know, we saw after compounded monthly, you don't get that much more money. Okay, like this was compounded monthly, 261, and if you know, we're going back to the last video, compounded continuously, you picked up about 10 more cents. So, you know, again, this is like a theoretical thing, but really it's pretty close to, in fact, it is what you would max out at, no matter how much you compound your interest. Hey, again, let's do one more example of this. Again, it's a plug-in. Right now, your principal is 2,000. I'm going to multiply by E. And the power 4 1/4, just be careful, that's 0.0425, that's 4 1/4. So I think half the battle is just changing these decimal fraction or percentages to decimals. And that's for 15 years. And what does this shake out to? 37.83. Sure, I'll go down to the penny, 49. We'll be super accurate. Okay. And just a couple problems here with E in them. You know, in math, we try to solve equations. Basically, E is something you want to either try to factor out or cancel out. Here, this is a quadratic equation, so I'm going to try to get everything to one side of the equation. So I would subtract this 4e to the 3x, set it to 0. Of course, here I have a common factor. That's the whole deal. Try to factor out E as much as you can. And I'm left with x squared minus 4. And boy, that should look familiar, right? But basically, you have two things that multiply to 0. So you'd use the 0 product property and say, hey, either e to the 3x equals 0 or x squared minus 4 equals 0. I can do this part, and so can you, right? This would mean x would have to either equal plus or minus 2. That's pretty easy, right? Difference of squares. This one, by the way, e is an exponential. It's never going to hit 0, right? So this part doesn't really solve to anything, right? There's a horizontal asymptote at 0. Furthermore, you can't take a number, raise it to a power, and somehow get back to 0. It just doesn't happen. So this only has two solutions. Finally, at the end here, I just wanted to solve a couple random problems from Algebra 2. Remember the goal when you're solving exponentials, if possible, get a common base. So hopefully these are rigged, and these are rigged to be a common base, right? 4, I can think of as 2 squared. 32, I can think of as 2 to the 5th. They're both perfect powers of 2. And of course, 4 is 2 squared, but you still have that 3x plus 1 as an exponent. You have a common base. So guess what? You can just set the exponents equal. So you have this 2 times 3x plus 1, equals 5. And then, solve it like a Algebra 1 problem. Distribute the 2, right? Subtract the 2, so you get 6x equals, 3. Here, x shakes out to be a half. And again, I'm going kind of fast. Feel free to use the pause and rewind button. Same thing over here, right? This is obviously a common base of 5, so that's 5 squared. We still have an x up top. And don't forget, square roots are the 1/2 power, so that's 5 to the 1/2. Again, once you get a common base, you could set the tops equal, set the exponents equal. So 2x would be 1/2, and if I divide by 2, x is 1/4. So, when possible, get a common base. All right, take care, guys.